Thanks, Emily, for the introduction. Hi, this is Yu Jiang from Saarland University in Germany, and today I'm presenting Embrogami, which explores shape-changing textiles with machine embroidery. So digital fabrication tools has enabled rapid prototyping of custom objects, and then among these tools, machine embroidery offers very unique benefits for creating integrated and entirely textile-based patterns on soft fabrics by performing programmed stitches. So I'll briefly go over how machine embroidery works, which is quite simple and beginner-friendly. So you have a base fabric on which you want to embroider the patterns. The base fabric is held in place by a tape-like stabilizer and a hoop that mounts the fabric onto the machine. Then, based on the user imported vector design file, the machine programmatically stitches threads into the base fabric to create the patterns. And then after embroidery, the stabilizer is torn away so the user has the embroidered base fabric, which is still entirely made of textile, thus very soft and durable. So using its capability to create integrated textile patterns, machine embroidery has been used to create functional textile surfaces such as ice-free interfaces and textile sensors by embroidering with conductive threads. However, current embroidered surfaces remain largely static and flat, with only slightly indented surface textures. We then want to ask if it's possible to have embroidered textile surfaces with significant out-of-plane shapes and shape-changing capabilities. This would allow embroidered surfaces to produce much more expressive and three-dimensional information to extend their affordance and interactivity. So an existing common approach to create out-of-plane shape changes on textile surfaces was to 3D print plastics onto a surface that can later form shapes above the surface through SMA actuation or contraction of pre-stretched fabrics. However, adding external plastics onto the surface compromises the garment's wearability and makes them less durable and washable, since the rigid plastics might fall off during wear. With machine embroidery, we want to explore achieving shape-changing textile surfaces that are entirely made of yarns and fabrics to retain their soft and durable form factors. So Embrogami thus contributes volumetric shape-changing structures on textile surfaces to create interactive garments that are easy to fabricate with machine embroidery, integrated directly into the base fabrics, and preserve the fabric's thin, conformable, and stretchable materiality, and versatile in their functionality with a set of proposed Embrogami structures that can vary in their size, shape, elasticity, and layout. With this, we hope to push towards highly wearable and also highly functional interactive garments. So first, I'll present our design and fabrication approach that allows us to create the principal shape-changing primitives. We realized out-of-plane shape changes through bistable origami folds that buckle out-of-plane by embroidering on pre-stretched fabric. So when you embroider two adjacent patches on pre-stretched fabric, the fabric around the patches would contract and cause the patches to naturally fold downwards to create a valley shape. And then by applying some external force, such as manually flipping the fold, the patches can also fold upward to create a mountain shape. Now let's take a closer look into how these patches fold to make them applicable for user interactions. So the natural downward folding by embroidering two patches is caused by the asymmetric layers above and below the base fabric. As shown here, an embroidered patch has one layer of thread above the base fabric, while below the base fabric there's a stabilizer and another layer of bobbin thread. As the layers below are thicker and also stiffer, which means there's more resistance to fold upwards, the patches will naturally fold downward to minimize the resistance. However, in order to make Embrogami structures interactive, they need to afford external inputs such as finger pressing or contacting with other objects in user interactions. Thus, based on our explorations, we sandwiched these two patches with two additional thin ones to create default mountains that can naturally fold upwards. The altered downward folds creates a larger strain and will force the middle patches to bend upwards to create a mountain shape. This enables Embrogami structures to change shape from mountains that rise above the surface to valleys that extend below the surface through user interactions. Now, after being triggered, Embrogami structures need to be reset to their default mountain states to prepare for the next iteration. We present three different resetting strategies to offer flexibility when designing user interactions with Embrogami. So the valleys can be reset locally, globally through pulling the base fabric, which revert the structures to their default mounting states, or through embedding and actuating very thin and lightweight SMA to enable digital control. So Embrogami structures support user interactions in their entirely passive states through out-of-plane shape changes. But we also enable embedding lightweight actuation, such as the SMA, and sensing into the structures to make them compatible with existing digital interfaces and textile technologies. So for sensing, we sandwich the conductive fabric tape between the two embroidery layers and attach another conductive tape underneath to measure the change in capacitance. This allows us to robustly detect touch and state change, even when the structure is worn on the body with large movements. Relying on machine embroidery, our fabrication technique allows us to create changing volumetric structures by simply varying the 2D vector design files. We thus present a set of variations to make the basic shape-changing Embrogami structures more versatile, functional, and also customizable. So to make Embrogami structures aesthetically and also tactilely versatile, we vary the fundamental mounting structures to create diverse primitive shapes that offer various geometries and folding directions. In a game controller that we built, we used action-specific Embrogami shapes. For example, for moving around the space, we used directional primitives, and for chopping actions, we used a pointy primitive, which gives spiky tactile feedback. So similar to other Embrogami-based interactive garments, this game controller can be easily removed and then reattached to a different physical context. Or even re-stretched and flattened to seamlessly hide into the surrounding when the interface is not in use. We also enable turning the bistable structures elastic to allow creating more diverse UI elements, such as push buttons. This is achieved by constraining the downward folding movement through two different approaches that allows us to fine-tune the elastic forces and also provide flexibility in terms of fabrication. As an example, we created a wristband composed of 10 visually identical Embrogami structures, yet they are programmed to have varying tactile feedback. Each structure can be either bistable or elastic with different elastic forces. The wristband can be used to encode and user-defined information. Other than customizing single primitives, multiple primitives can also be composed to form a larger layout or to create more complex shape-changing behaviors. I'll show two examples here, and please check our paper for more detail. Firstly, individually functional and non-interfering primitives can be juxtaposed in a larger layout to work as a pixel display. In one of our applications, we uniformly laid out the primitives in a 4x3 arrangement to form a passive display that can be used as a boxing training patch. When contacted with external surfaces or objects, the patch can visualize the contact area through shape changes that are triggered by the external force input. The patch can help with posture correction in different exercises such as kicking, punching, and dodging. Two cells can also be integrated to create toggling behaviors. Aligning multiple toggles together create a slider that can be user-triggered to show different shapes corresponding to the user input. For example, we use this slider and an additional button to build a top that allows users to control their running progress tangibly and without carrying additional devices. The progress slider on the arm allows the user to tangibly set a running goal before running. As the user runs, the slider is actuated with SMA to show real-time progress feedback. The top also integrates a button at the palm, so the user can simply clench the fist to start a break. SMA then actuates to reset the button when the break ends to signal the user. To support customization of Embrogami structures, we also provide a design tool. Users can freely select, place, and visualize the primitives on the canvas. They can adjust the size of the structures, or make the primitive elastic and fine-tune the elastic forces. They can also integrate the primitives by overlapping them at a certain embroidery patch. In the end, the tool generates SVG vector design files that can be machine embroidered. Finally, we conducted a series of technical evaluations to characterize the behavior of Embrogami structures to help with designing, deploying, and also extending known R structures. I'll show two experiments that we conducted, and for the complete evaluation, please refer to our paper. So firstly, we evaluated the scalability of our structures, which in turn allows us to customize the dimension. We parameterized the amplitude of the formed Embrogami structures based on the embroidering pattern and created autoplane folds with height that varies from 5 millimeters to 2 centimeters. Embrogami does have some requirements on the base fabrics, and not all fabrics can be applied. So to help users select the right base fabric, ideally also locally, we evaluated different fabrics based on their weight, stretch force, and the amplitude of the formed mountain structures. Our results indicate that fabrics that are more lightweight and easier to stretch create more prominent mountain structures. So to summarize, Embrogami presents a design and fabrication approach for integrating shape-changing structures into textiles with machine embroidery based on bistable origami folds. We contributed a set of functional volumetric structures with customizable shape, elasticity, composition, sensing, and also actuation to enable versatile user interactions, which is further supported by our design tool and a series of technical evaluations. We also demonstrated 4 example applications to show Embrogami's feasibility and potential in unlocking highly wearable and functional on-textile interactions. Lastly, I want to thank my amazing collaborators, Alice, Nargis, Jan, and my advisor, Yogan, for making this work possible. And with that, I'll conclude my talk. I'm happy to take any questions.
Hi, Cedric Honnête from MIT. I was curious if you had any idea of ways to make it a bit faster for the actuation? Maybe other materials than SMA or more?
You mean SMA-based actuation?
Yeah, or an alternative,
triggered...
liquid crystal elastomer like Fiber Robo or any other?
I think the only electronics-based actuation we tried is SMA because it's the most lightweight and small actuation method that we have at the lab, which is also quite easy to integrate into the textile directly. And with a very thin SMA that we used, it was also very safe for human skin or on the clothing. And I think one drawback is that it is quite slow to actuate. Yeah, I think it would be a future work to try other possible actuation methods, but we didn't try. But I think one benefit of Embrogami is it's compatible with other existing e-textiles, so feel free to try other things yourself with our structures, I think.
So nothing faster in mind right now?
What?
You don't have anything faster in mind right now?
No.
Any secret?
Not in my mind right now. Yeah.
Thank you.
Sorry.
Hi, I'm Jenny from University of Utah. Really cool work here. I was wondering if you experimented at all with mixing these Embrogami elements with sort of more decorative, non-functional embroidery, whether that had any impact on the behavior of these elements, for example, or any other interesting effects.
Can you elaborate on what
like
you mean by
imagine
decorative?
I just think embroidery looks pretty, so I want like little flowers on my shirt, but I only want like some of them to be like Embrogami bits because maybe I just want to have like, I don't know, like daisy chains or whatever, kind of like to make it look a certain way, but I still want to incorporate these elements. I imagine this would like affect some material properties, maybe at a very global level, but I was wondering if you'd thought at all about like the impact on the shape-changing effects.
So I think one of the benefits of Embrogami is that it's compatible all the machine embroidery things that you can do. For example, changing the color of a thread, or if you want to embroider more complex patterns on top of the patches, you can do that. And we did consider how different designs can affect the shape-changing behavior of Embrogami structures. So we tried to characterize, for example, when we evaluated how to lay out the different cells, like the gap you need to leave between each Embrogami structures to make them still individually functional. So that's one thing we tried to evaluate to make sure that for different designers, they can still maintain the structural stability of the bistable shape changes. And we also did similar things for combining or integrating other shapes. Yeah, you can check our paper for a more extensive technical evaluation.
Okay, thank you.
Okay. I am Atul from University of Copenhagen. Thank you for the talk. It's amazing. I was just wondering, have you thought about the scalability of this technique, like in terms of force and the size of it? You talked about a little bit about the force, but about what about the size, how big or how small I can go, and also in terms of force, like how much force feedback I can get, and maybe if you can.
I think force scales together with the size. I didn't characterize exactly how much, but so in the paper I only reported, as I show, like structures that with height that varies from 5 millimeters to 2 centimeters. But for myself, I also tried embroidering like very, very large, like 15 centimeters size of Embrogami structure. So what I found out is when the structure gets too big, the embroidered patch tends to curve. So that leads to a different shape other than the basic mountains that we present. I think it has future possibilities, but it basically creates a very cup-like shape that also takes a very big force to flip through, and that almost make it different from like a textile surface. Yeah.
Thank you.